What's going on? What's going on with the machine? You brought the computer?
Yeah.
Okay. Yeah, I got you that one. You might want to try to turn it on to see if that works. This one is not mine. This is from the laptop car. So this is just for the class. For today, it's charged. That one is already charged. Okay, so if you want to use yours, that's fine. Yeah, just give it to me, and I will send it to IT and see if they can. That's weird. I remember, like, it was created. This computer has some problem before you use it, and I sent it to them, and they did like a reboot of the machine. Okay. Those of you who are connected, I apologize. I'm discussing something with one of my students here. So we'll be getting started in 3 minutes. So I'll be here and I'm going to start sharing my screens in the next couple of minutes. Hey, good afternoon. It's 2 o'clock, so I'm going to start sharing my screen. Those of you who are connecting, good afternoon for you too. And today we are gonna start our second lab or our second modeling lecture on Arena. So this is gonna build on top of what we learned last time. Focusing today on generating some of the statistics that we are going to be collecting using Arena.
So we're going to spend some time discussing the different type of statistics that can be collected. And also we're going to state the difference between a single replication and multiple replications. So how can we generate multiple experiments? Remember that the idea when you build these simulation models is to get a solution or test different improvement strategies when you take into account the uncertainty in the system, the variability in the system. So those are the type of things that are very difficult to model using a just a mathematical model. Like if you build an optimization model, for instance, if you want to take into account the variability in the system is very challenging, it's very difficult. Typically what we do is just we assume a deterministic approach in which we assume that everything is certain. Like we know that it's going to take 5 minutes to complete a part, which in reality that's not the case. It could take 5 minutes, 6 minutes, 7 minutes. A failure can occur in the machine, and that would impact your processing and your process. So simulation is a tool that helps us study systems from that perspective. We want to make decisions and we want to take into account the uncertainty. So that's why when we model these delays, we use probability distributions, because we are taking into account the variability that is embedded in the system. Same thing for the interarrival times. So we are just not assuming that we're going to get a customer every 2 minutes. We know that we cannot have a system, such type of system, reality. There's an uncertainty in terms of the arrivals of the customers. There's uncertainty in terms of the arrivals of the parts. There's uncertainty in terms of the demand for the product. So all those things are captured with the simulation models. So in the same way, when we look at the input, everything that I just said is related to the inputs. But when we run these experiments, we want to test our system using different scenarios. Meaning that in one case, our system will be reacting to an arrival process, but then when we run a second experiment, we are giving the system a different arrival pattern. And when we run a third experiment, we are giving the system a different arrival pattern. And when we do this multiple times, we are basically studying the robustness of our system under different scenarios, different arrival patterns. So our decisions at the end are made under the consideration of all these different patterns that are observed in our system. So we know that the decisions that we are going to make are going to be good for these different things that can happen in our system. So our output analysis have to be aware of those things. I mean, we are not going to look just at one single experiment. We want our conclusions or recommendation to be based on this, I don't know, multiple number of experiments that we are taking into consideration, so we can give a recommendation that is robust. Is based on these different evaluation of different scenarios and is taking into account the variability of the system. So let's see. So this is lab 2. And again, we are going to be looking at different, we're going to add to our discussion. So we started with the definition of this. So I'm not going to go through that today. I'm going to focus on the new things. But remember, every time you build a model, that you save it, you put it in the save location, so you don't lose your work as you are building your model. So so here's some additional information. We went through this make sure that you put your names and that you use the Simon summary report as the output file. And we're gonna be looking at the replication parameters today. So we talked about the resources already in our previous lecture. We talked about the importance of defining this experimental frame in which we are going to determine, or we're going to state how many resources and the name of the resources and the capacity of each resource, meaning the number of identical units that we're going to have. All that is going to happen in the experimental frame. And then after defining the resource name and the capacity in terms of identical units, we can build the model. So in order to represent a resource, this could be a machine or it could be any type of resource that you have in your manufacturing facility. Using 3 blocks, the seize, the delay, and the release. And typically we also put the queue in front of it. So if the resource is busy or occupied, we can generate a line in front of it. So it's gonna wait, all those entities are gonna wait until the resource become available. So what are the new modules for today? We are going to look at attributes for the first time. So if you remember, from our initial discussion, we have attribute in the terminology is a property of an entity. And something that I mentioned multiple times is that once you assign that to the entity, that property is not going to change. So if I assign a number to that property, that number is going to remain with that entity through the duration of the model simulation. If I assign, let's say, a color to that entity, that color is not going to change. It is going to remain with the entity through the duration. So we're going to be defining some attributes today. For example, part type. Let's say we have 2, 3 different part types in our manufacturing process. 2 parts. Let's say part 1 and part 2. And we want to assign that attribute to these entities. I'm going to mark this entity as part type 1, and I'm going to mark this entity as part type 2. Then that attribute is not going to change. Everything, once you assign an entity a part type, that's going to follow the entity through the duration of the simulation. So you can use that information. Let's say when this entity arrives to a specific block, you can call that entity, and if you want to collect statistics about that part type property, you can do that. So we'll see how that works today. And how are we going to define and assign these attributes? We're going to have a experimental frame, an element block that is going to allow us to define the attribute, that property of an entity. And then whenever we want to assign that property to an entity, we're going to use an assign block, and that's in the model. So the assign block allows us the assignment of a value to a user-defined entity attribute. For example, if I want to assign the arrival time of a customer of an entity to the system, I can do that using an attribute. Say this is the arrival time, and I'm going to assign the time using this this system design variable called tnow, which has the current clock time and is used to calculate the cycle times. Attributes, we're going to assign property of an entity. For example, priority, type, arrival time. Suggested naming scheme, we use the lowercase first word, no spaces, and then uppercase first letter of the next word. We're also going to be making decisions in our model. So for those purposes, we have, if you're familiar with flowcharts, is the same idea. If you have like a decide block, if statement, in Arena, we have a branch. So the branch is going to use an if statement to split the arrivals or split the entities based on a property. So for example, if you have part types, we can split the entities and send them to specific routes based on the type of part that you have assigned to that entity. So if it's part type, in this example here, we have a branch with 3 branches. For the first branch, we have the properties say part type equals 1. So if the entity is part type 1, then it's going to take that branch. If it is part type 2, it's going to take the second branch. If it is part type 3, it's going to take the third branch. Typically, we have also a nails branch. So if it's not meeting any of these 3 decisions, then you can send that through the else option. Something that I want to mention that is very important, can create errors in your model if you don't do this correctly. You have to assign a 1. Once you double click in this block, you'll see this window, the branch block window. You have to make sure that that maximum number of branches that each entity can take is equal to 1. Because if not, then an entity can be duplicated, it can take multiple branches. So just to make sure that each entity takes a single branch, you just put a 1 there, and that's why I'm marking this as in red. So make sure that that's always there. Okay, so that's in terms of the logic. These are the 2 major things that we're going to work with today: the attributes, in assigning attributes, and also the decisions. So how to use this branch block. The other thing that I want you to start working with today is the statistics. So you already used the counter block to count the number of entities. Today we're going to use some new modules. One that is called the tally block. And then we're going to also consider the time average statistics or time persistence statistics. So I'm going to show you what's the difference between them. Tally is a data for which there's an arrow first, second, third observations. Since values of them are tallied when they are observed, Arena called them tally statistics. So for example, when we discuss a tally, it's like having a bag. So essentially what you do with a tally is that you collect data points, and then once the simulation is completed, you use those data points to compute statistics. So for example, let's say you have a process that is like this. You have input, output, and you have a resource. So you have a create, and then you have a dispose. And let's say you want to compute the cycle time for your entities in the system. So what you're going to do is that you're going to start collecting some statistics here. We're going to use a tally. And what this is going to do, let's say you're looking at the cycle time. Every time an entity, say an entity goes through this portion of the model, you are going to add an observation to a bag. So for example, this first entity was 10 minutes inside the system. So your first observation that is going to go to the bag is 10 minutes. Then another entity crosses that block, and that one stay in the system 9 minutes. So now that's going to go into the tally, going to say 9 minutes. Then you have another one that crosses that block. So you're tallying those numbers. Say at the end you got all these observations into this bag
which is the tally. And then you can use this information to compute average, or you can compute the standard deviation, or you can compute confidence intervals. So you have all these data points, and then you're going to use all those data points to compute some of statistics from your system. That's what we call a tally. Anything that you can measure and put in the bag, measure, you put in the bag, you measure, you put in the bag, is considered a tally. For instance, the cycle time. But there's another type of statistic that is called a time average statistic. And this is different. For example, the working process. The working process is something that is depending on the time that you are making the observation. Right? So if you, for example, this is 1, 2, 3, 4, 5. This is WIP. Working process are the parts that are inside your facility at any time. So if you have time here, 1, 2, 3. So this, let's say this is 7 a.m., 8 a.m., 9 a.m., 10, 11, 12 p.m. So time persistent statistics are those statistics that are changing across time. So you don't have a way to measure them from beginning to end. These are statistics that are going up and down through the duration of the simulation. So this goes like this. So the way these are computed is different. They're computed based on the area under this curve, and that's depending on time. So those statistics, for example, working process, utilization of the resource, it's also depending on time. Those are called time average statistics or time persistent statistics. And we need to understand how to differentiate them, okay, because they're computed differently. Okay, so that's, and I'm gonna start telling you, okay, counters, utilization, working process, time persistent statistics, tally statistics, cycle time. So we'll see those through the examples. So time average statistics are weighted average of the working process weighted by the proportion of time during the run that the system had that WAP. For time persistent statistics, we're gonna use this user-defined, software design variable. This is defined by Arena to obtain the average across replications. For tallies, we have TAVG. Okay, so that's why we need to be able to differentiate between them. If we are going to be computing average across replications for the tally, we have to use TAVG. If we're going to compute the average across replications for a time average statistics, we have to use DAVG. So to define the tally, we use the tally's elements. This is used all information needed for tally blocks in a Simon model. In a tally block, this block tallies the complete set of internal costs and time attributes for the entity. For example, cycle time, cost. And for the cycle time, we use this software defined the variable called T now. One more thing that we're going to use to collect statistics today are the sets. So we are going to define a group that might be referenced via a common name and a unique index. This can be used in combination with tallies elements. So you'll see how this works today. These tags
These are used to obtain time persistent statistics in a discrete system. So for example, resource utilization, working process, and so on. Then finally, remember that I began today discussing the importance of simulation to consider multiple experiments so we can make recommendations. So in order for us to generate multiple experiments, we're going to use the replications. So we want to run this experiment 10 times. So we want to run this experiment 100 times. So those are replications. These are use several independent, statistically identical runs and investigate how the results change from run to run. Each run uses separate input random numbers to generate the data used to drive the simulation. For example, the arrival times, the service times, those are independently generated for each replication. So we're going to use the output element to define the statistics and the performance measurements that we want to collect from our system. And that's going to generate an output report which summarize the values of the performance measures for all replications. So this is an example of when we are looking at, for example, in this report, we have an output summary for 10 replications. So this is for 10 experiments. And you see the average output includes, or the statistics for each performance measure includes the average, the half-width for the confidence interval, the maximum, and the minimum. If you just run one replication, you will not be able to get the confidence interval, the minimum, and the maximum. This is only reported once you have multiple replications. Okay, so let's try to work with an example. See if we can see this in practice. So today we're going to have a similar model like the one we had in the example last time. But today we're going to have two drills and two different types of parts, right? So you can see here there's we still have an interreliable time of following an exponential distribution with 4.4 minutes. But now we have two types of parts, A and B. 60% of them are going to go here to drill one, and the rest of them, 40%, part type B, are going to go to drill number 2. So we have the processing times for each one of these drills, and this is what's going to take us more time today. I want to collect all these or answer all these questions. We're going to run 10 experiments. Let's say for 8 hours, and then we're going to collect all these statistics. So average cycle time for all parts, average cycle time for part type A, average cycle time for part type B, average utilization of machine 1, and the average number of parts completed. Okay, so let's work with this. So you can open Arena. Can you see? Okay, good. So I know that something is covering some of this. Okay, so let me save this, save as. And as always, I start by creating or differentiating between the model frame
and the experimental frame. And we're gonna keep using the blocks and elements. So we need to attach those blocks.
We have to add properties.
Yes. Yes, for now, then we're gonna transition to the others. We're gonna do, I think, first 4 labs are gonna be with blocks and elements. Okay. So I'm gonna start defining some of the elements or my experimental frame. So I know I'm gonna have 2 resources. So I'm gonna be needing some cues. I need to increase the size. Where's the zoom? Let's, so I need to make this smaller, I guess. I have the experimental frame. Okay, some cues, some resources. So elements, pull the resources here. I'm going to be collecting some statistics. So let's start with the counters. We talk about the attributes. Also, we're going to be using some tallies. And that's for the tallies. We also talk about the dstats. Let's look at the sets too. See what else, and the outputs. So we need all these blocks to define our experimental frame. 4, 5, 6, 7. We need the cues, resources, counters. So these counters, tallies, these stats, these are needed for the statistics. Okay, so counters, tallies, these stats, sets, and outputs are going to help us define our statistics. So we have 2 machines. So I'm going to define 2 queues here. I'm going to call this one, I don't know, let's make it simple. Q1. And then another one, Q number 2.
And both of them are first in, first out. Okay, so I'm not changing the policy or the ranking criterion. First entity goes in, that's the same entity that goes out first. Okay, so we have two queues, Q1 and Q2. And in terms of resources, we have two machines. So, yes, sir. That again?
The Q1, the translator, you have made it small.
I typed the word again. Did you type it completely? A Q non-space one. See. For the resources, you're gonna do the same thing. Gonna have two machines. So I'm gonna change this name to machine one, no space. Capacity is gonna be one, only gonna have one machine. So I'm gonna click OK. This is wrong, sorry. It should be machine instead of whatever I wrote there. So machine one. Then I'm gonna add another one. This is machine two. Would it be better if I turn on the lights or want me to turn it on? Better now. Okay. We get machine one, machine two, capacity one for both of them. I'm gonna have two attributes. So I need to define them here. The first attribute they're gonna use is called arrival time. So I'm writing the two words together, arrival, and then to differentiate between the two words, I'm using a capital letter with a T, arrival time. And then I'm gonna add another attribute that I'm going to use. This is called part time. Same thing, part, lower letters, and then type, capital letter T. Okay, so yes. String are non-numbers. So real is when you use numbers. String is when you're using letters. Yeah. Yes. So for example, if you want to assign instead of a number, like part type A, B, C, yes, yes. But for now, I prefer to keep everything in terms of it's easier from my perspective to keep it with the numbers. Good question. Part type, arrival time. Okay. Let's see. We're gonna be counting right? At the end, we need to know how many parts were completed. So let's add a counter here. That is called parts completed. In terms of the tallies, if you look at the questions here, I mentioned that cycle time is computed using a tally. So we have 3 cycle times that we have to compute: the overall cycle time, which is for both part types, and then the cycle time for part type A and the cycle time for part type B. Okay, so we need to define 3 different tallies here. So gonna add here cycle time. This is the overall cycle time, or the cycle time for both. And then I'm going to add cycle time A. I'm sorry, let's use lower little here, cycle time A. And then cycle time B. Is it A and B or 1 and 2? Yeah, so I'm gonna be using 1 and 2, but 1 is A, B is 2. Okay. Okay. Right, because this is the description, A and B. Okay. What else? Okay, so I'm going to leave this for later. These 3. Let's save this for now. And let's start building our model. So let's go to the blocks. We are going to create some entities. So the arrivals are going to follow an exponential distribution. So we can type expo 4.4 as the inter-arrival time. So this is going to create some entities. And from here, we're going to assign some attributes. So I'm creating these entities, and I'm going to start assigning some properties to these entities before they get into the model or into the actual manufacturing process. So for that, I'm going to use, again, if you look at this here, we defined the attributes, right? So we define the attributes part type and arrival time, and we're going to use an assign block to assign those attributes. So let's go here, find the assign block. We're going to connect that to the create block. So double click on the assign block and let's add. So this is going to ask you if this is a variable or an attribute. Okay. We know we're going to be using attributes. We already defined the name of those attributes. So let's start with the first one, the arrival time. So we're going to have to type the name again, arrival time. And the value you remember, we have a software defined variable, a software defined, yes, variable that is used for these purposes. The value will be that T now, software defined variable. So what this is going to do is every time an entity crosses this block, it's going to call this T now. The T now is going to say, okay, it's 10 a.m. in the simulation. It's going to assign 10 a.m. to the arrival time of this entity. The next one is the part type. Okay, so I'm using the same name. This one, the example is telling us that 60% is type A, 40% is type B. So I'm going to use a discrete distribution. So I'm going to build an expression here with a random distribution that is discrete. And remember that this is cumulative. Yes. Right, so it's 60% one and then 40% two. So we're gonna make this 0.6, comma, 1, and then the rest 0.6 plus 0.4 is 1, and this is type 2. So the discrete probability distribution is gonna be 0.6, comma 1, comma 1, comma 2. And that's based on these probabilities, 60% type 1, 40% type 2. And that's going to be the value for this. So every time an entity crosses this, the software is going to create a uniform random distribution. You're going to generate a random number from 0 to 1. So it generates 0.75. 0.75 is greater than 0.6. So it's going to assign part type 2 to that entity. And the next time an entity crosses the block, there is another random number, 0.3. 0.3 is between 0 and 0.6. So it's going to assign 1. Again, that's what it does. Every time an entity crosses, generate a random number that is between 0.0 and 0.6, it assigns a 1. If it is between 0.6 and 1, it's going to assign 2 to the entity. Okay, and then we can click OK. And from here, we're gonna split these parts according to the part type. So I'm gonna double click this. Remember, this has to be 1, so it is already there. And we start adding some branch types. So the condition that we're going to use, if part type, part type equals 1. That's going to be, we can send this to label. We're going to learn how to use that later on, but for now, we don't have to worry about that. Basically what it does, if you see every block that you open at the top has a label. So if you assign a label to a block and you want to just use that label here, it will send that directly to that block. But for now, since we are learning, let's just use the connectors. So if part type equals 1, then it's going to be moved through that branch. Yes. It is automatically defined. You have what? Oh,
Yes, so we want to use the entity indicator. And then we can define another branch with part type equals 2, but since we only have 2 part types, we can just say else. So that's what we're gonna do. You can just put an else here. So everything that is not part type 1 is gonna go through this else branch. And when you complete this, you'll see that there's gonna be 2 triangles. So the first triangle is for the condition, and this one is for the else.
Professor, I just had a quick question just out of interest.
Yes, go ahead.
Yeah, so does there have to be an else branch? Will it throw an error if there's not an else branch? Or is it okay if we did 2 ifs? Just wondering.
So, I mean, you can define another branch for part type 2, and it still works. But we want to have 2 branches so we can split them.
Oh yeah, I was just wondering if it required an else block for if statements or not. But yeah, it sounds like it doesn't. Okay, thank you.
Yeah, no problem. So now we are going to the logic of the machines. So let's go back here to Zoom. Okay, so let's build the logic for each machine. So for each machine, we're gonna need a queue, seize, delay, release. So queue, seize, delay, and release. And since I know I'm gonna need 2 of this before I edit anything, I can just copy and paste this logic. Okay, I can do this before I edit. If you already edited it might create problems. So these are empty blocks. So I'm just copying and pasting those empty blocks. And I will go to home here, and I connect part type 1 to the first one, and the else block to the second. Okay, so now we can look at the queue for the first. And since we already defined names, we can just look for the right name here, Q1. There's no capacity associated with this one, so we can just click OK. And then we're gonna seize, gonna add here machine 1. Number of units to seize this machine is 1. The delay is given by a triangular 3.2, 4.2, 5.2. So I'm going to go here. We can build that expression
by looking at the random distribution triangular. You're gonna put the minimum, the most likely, and the maximum. So 3.2, 4.2, 5.2. And then click OK. And then we're gonna release that same machine. So we're gonna add here, and we're gonna release machine 1. And now we're gonna go through the same process with the second group. This is gonna be Q2. We're gonna seize machine 2. Excuse me. And then the processing time is 3, 4, 5, it's triangular. So I'm gonna build another expression here with a triangular distribution. Three, 4, 5. And now we're gonna release machine 2. Okay. So now we want to count. So let's count the number of parts that are completed. So I'm gonna look for a counter here. And I'm going to connect both of them to this counter block. So we have the counter ID already. This is part completed. And the counter increment is 1. So that's not gonna change. Ooh, I'm running out of battery. Apologize for that. I'm glad that I was able to connect before running out of battery. So, okay, so let's continue. So the counter is parts completed. So this is gonna count all the parts that go through this. Okay. Okay, and we have the tallies to collect the cycle times. So let's do this first. Let's check that everything is making sense so we can add a dispose block at the end before we continue with the statistics. So let's connect these two. You want to check. No. Okay, so we have some modules that haven't been edited. I guess these are these 3. So let me save this. I'll remove these 3. I will bring them back in a minute. So let's see. Check the model. It looks like there's no errors. So if you remove the other 3, Any errors after removing those? Nope. Good. Okay. So let's work with the tallies. So I'm going to add some tallies here. One for the cycle time. So I'm going to double click in that block and I'm going to find the cycle time, just the one that considers both part types. And I'm going to state the expression that is going to allow me to compute this. So what I want to do now is I want to get the time when the entity arrived this block, and I want to subtract the time of the arrival. Okay, so that expression is going to be T now minus the arrival time. So every time an entity crosses this block, it's going to go find the time right now, and it's going to subtract that attribute that the entity was carrying, which is the arrival time. And that will be the cycle time. Yes.
Everything
The arrival time is assigning a time to that attribute. Okay, so it's just telling, you went through this block at 10 a.m. simulation time, and I want you to store that 10 a.m. inside of you. So when I need it, I can call that number. Is the arrival time. The arrival time is a number, is a time. Okay, it's just stored under that attribute. And now you're calling that attribute, that time. So if 12 now, and then the arrival time was 10, the difference is 2 hours. Okay, good. So now but we also need the cycle time per part type, right? So let's see how can we deal with this. So in order for us to work with this, we can do this 2 ways. We can add another branch, split the parts, and then collect the cycle time individually, or we can use a set, which is faster, less complicated. So let's define a set. We need to go to the elements and find the sets. Double click on it, and we have to give a name to this set. I'm gonna call it cycle. Let's just call it CT by type. CT by type. And then we need to state the members of this set. The members are gonna be cycle time A and cycle time B. We need to use the same. If you use lowercase, uppercase, Arena is case sensitive. So we need to make sure that we use the same names with the capitalization in the right place. So now we are defining this set, CT by type, and this set is gonna have 2 members, cycle time A, cycle time B. So CT by type. And now I can go here. Sorry, I will need to add another tally. Need to add another tally. So go back to the blocks. Bring another tally to your model. double click on that tally. And here we're gonna state the name of the set, CT by type. And we're gonna open a parenthesis and we're gonna put the name of the attribute, part type. And the value is gonna be T now minus the arrival time. Okay, so this is a little bit more involved, but the idea is for us to avoid having this other logic to the branch and separate tallies and so on. So this make things a little bit less crowded, I will say, but it requires some practice for you to remember how to do this. So you have the tallies, you create a set, you're gonna put these two tallies as part of this set. So you have a set of tallies. And then when you create this tally block for collecting the statistics, you use the name of the set with the attribute that is used to differentiate between these cycle times. And that attribute is the part time. And then the value is the same, T now minus the arrival time. Let's click OK. So you have CT by type. What else? So I think that covers all the model. You still need some statistics. Yes, sir. Let's see. So when you do the check model, it's not working. Yeah, so sometimes Arena will allow you to do the automatic connection. Sometimes you have to do it manually. So check if you have any errors. See. Okay, so there's some additional statistics that we need to collect. The problem is asking us cycle times. So we got those. We got the number of parts completed. The only thing that is missing is the utilization of machine one. So to collect the utilization, we need to use one of the utilization again is a time persistence statistic. So we have to use this stat. These stats is part of the elements. So I'm going to bring these stats. And I'm going to define, I think for the previous lab, you needed to collect the utilization. And I asked the students who asked, I asked them to click on the report for resources that should give you the value. Today, I'm going to show you how to collect or how to compute the statistic. So you need to do the dstat and you're going to use this software defined variable in R and the name of the resource. So in our case, it's machine one. NR machine one under this stat. Okay, so let's go to the, save this again. Let's go to the setup
we want to run this for 8 hours, base time units in minutes. The run control reports. For the reports, remember to select the Simon summary report. And for the project parameters, I want you to uncheck all these things. So nothing needs to be checked now. So let's go through this one more time. This is not changing. This is not changing. The report, I want the Simon summary report. For the project parameters, uncheck everything. Replication parameters, let's do one replication for 8 hours. Base time units, minutes. And the rest should stay the same. So let's click OK. And let's try to run it. Okay. So were you able to get the same results?
Yes.
Okay, good. Yes.
Yeah, because we are asking for a few months.
But if you want to see machine 2, you can you repeat the logic. Yes. So okay. So this is just for one replication. I remember what I did. I spent the first part of the lecture discussing. Okay, now one replication is just looking at one scenario. But that's not enough for us to make decisions or to make recommendations. We want to put this system into different scenarios, different arrival patterns, and see how robust the system is under the uncertainty. So for that, we need to run multiple replications. Okay, so for example, if we go here to the setup, we can stop here and go to the setup and change this to, let's say, 20 replications. And then click apply. If you run this again, it should take more time to run because it's running 20 experiments. And when we click yes, you see that now you're going to get results for each replication. So replication 2, replication 3, replication 4, 5. So everyone is going to give you a different number. And some of them will have the same number of parts completed, but you'll see that every time you change the experiment, there should be some changes in the results because you're testing different arrival patterns, you're testing different processing times, and so on. Okay, so we have the results for all experiments, 20 of 20, but we don't have a summary of the results. Now we want to see, okay, now that you perform all these experiments, give me a summary of all these experiments. Basically, what we are asking is, take the information from these 20 experiments and compute the average, compute the confidence interval, and compute the minimum and the maximum. So we can generate such a report in Arena by doing the following. We're going to go to the elements and we are going to call this block called outputs. Okay, and we're going to double click here. So what we're going to do now, I'm going to ask the model to give me the average for each one of the statistics, the average across replications. So I'm going to start with the cycle time. I'm going to use this user-defined TAVG, I'm sorry, software-defined variable TAVG that is coded in Arena to generate the average across replications for the tally. So that's why T. T is because it's a tally. TABG, average across replication for the tallies. And I'm going to put the name of the tally here, cycle time. And then I'm gonna close the parentheses. And I can give it a name. So this is average cycle time. So this name is for the report. This is how the performance measure is gonna be listed in the report. Average cycle time, AVG cycle time. I'm gonna do this same thing for the other two. This is gonna be TAVG, cycle time A. And the name is gonna be ABG, or average cycle time for part type A. You're gonna do the same thing for the other one. TABG. Cycle time B. ABG cycle time part type B. Then I can do the same for the counters. But for the counter, I need to use a different variable. This is called NC, open parenthesis. What's the name of the counter? Parts completed. And the name is average parts completed. So in the name, I'm using this average. I just want to highlight that this is the average across replications, right? So for each replication, we are getting a report. Now we are creating this final report, output report for the average across replications. Average part completed. And then there's one missing, and it's for the machine utilization. And the reason I left this one to the end because it requires some additional work. So let's click OK for now, and let's run this. Now you got the report. If you go to the end, you'll see, and now you get this nice report for the outputs. Get the average cycle time for part type A, average cycle time for part type B, average parts completed, average cycle time. So you get the average, you get the halfway, which is the confidence interval, minimum, maximum for 20 replications. This is going to be important. Second. Because when we start comparing designs, we need to look at this. We need to look at this to differentiate if this design better than this one. Okay? If these statistics are overlapping, we cannot say that one is better than the other. But if these statistics are not overlapping, we can say, okay, this design is better than this. Yes, sir. Yes. I can share with you mine, so you can double check what's going on with this one for yours. Conflict is when you compute the confidence intervals. You have the average and you have plus minus 2 times the here. Those are different type of confidence intervals. Let me show you. The plus minus z times standard deviation divided by the square root of n, which is the sample size. So this is used to measure the variability in your results. See, this everything that we are doing is probability based. So we cannot say, okay, the results are exact numbers. We need to give an average and we need to give some bounds. And the halfway is completely bound for the confidence interval, this plus minus. Okay, so when we report the average and we report an upper bound and a lower bound based on this summation or subtraction. Okay, so we'll talk more about this later, but that's the idea. So I need to do one more thing before we go. Is computing this average for the utilization. So, the idea here is that you need to go a step further to get the output for the utilization. You have to give a name to this expression. And you need to use that name to compute the output report. So here I computed the utilization in our machine 1. I have to give this a name, machine 1 utilization. And I use this name, control copy. When I come here, at the expression, this is going to be a DAVG because this is a time persistence statistic. And what you're going to put inside the parentheses is that name, machine 1 utilization. Okay, so this is going to be AVG machine 1 utilization. So if I run this now, you get the average machine 1 utilization at the top. And that's the last statistic. So if you see, we have 5 performance measures here. Those 5 performance measures are to answer these 5 questions that we have here. Any questions? So Palaniapan, send me an email. I will send you the model so you can check what happened with yours. Is there any other question? Good. So stop here. You have a second lab to work on. So make sure that you start looking at that. If you have questions, we can talk about that on Wednesday during our lecture. Now then, I'm going to stop here and I'll see you Wednesday.
Thank you, Professor.
Thank you, Alexander.